All right, let's dive in. Today, we're going to pull back the curtain on one of the most fundamental algorithms in all of operating systems, round-robin scheduling. You could say it's the secret sauce that makes modern multitasking even possible. I mean, have you ever really thought about that? You've got your music playing, you're compiling some code, your browser has 20 tabs open, and it all just seems to be happening in parallel. But here's the thing, on a single CPU core, that's not quite what's going on. It's actually this brilliant illusion. It's like a high-speed magic trick, really. The operating system's scheduler is switching between all those tasks so incredibly fast. We're talking milliseconds here, that to us, it looks like they're running all at once. This whole concept is the very heart of what we call a time-sharing system. So here's our game plan for today. We're going to start by really understanding that multitasking illusion. Then we'll meet our main character, the round-robin algorithm. We'll learn the rules of the game, see it in action with a real example, figure out how to judge its performance, and then wrap up with the super important time quantum trade-off. Okay, so if the scheduler is in charge, how does it decide which process gets to run and for how long? Well, there are a bunch of different ways to do it, but round robin is famous for one thing above all others. It's absolute fairness. At its core, round robin is basically first come, first serve, but with a crucial twist. Every process that's ready gets a turn, but, and this is the key, it only gets the CPU for a tiny fixed slice of time. When its time is up, the OS forcibly interrupts it. That forceful interruption is a concept called preemption. And that little slice of time, that's called the time quantum. Think of it like a timer. Once that timer goes off, the OS hits pause, saves everything the process was doing, and shoves it to the back of the line to wait for its next turn. This ensures that no single process can just hog the CPU all to itself. So you might be wondering, how does the system keep track of all this? To really get the mechanics down, we need to look at two key tools: the waiting line for all the processes and the scoreboard that shows us who's running and when.
First up, we have the ready queue. This is literally the waiting line. It works on a simple first in, first out principle. When a new process is ready to go, it gets added to the back. When the CPU is free, it always grabs the process from the very front. Keeping this line in order is absolutely critical.
And next, we have the Gantt chart. This is our visual timeline, our scoreboard. It's going to show us exactly which process is using the CPU at any given moment. By the end, it tells the entire story of how everything got done, from start to finish. Okay, theory is great, but let's make this real. Here's a set of 4 processes we're going to work with. You can see when each one arrives and how much total CPU time or burst time it needs. And the most important rule for our little system, the time quantum is set to 2 units. All right, this is where the magic happens. We are going to build our Gantt chart and manage that ready queue step by step. So you'll want to pay close attention to 2 things: the clock and the order of the processes in our queue. Okay, at time 0, the clock starts. Who's here? Only process 1, so it's easy. P1 gets the CPU. It runs for its full time quantum of 2 units. It needed 5, so it now has 3 units of work left to do. Now it's time 2, P1's time is up. During that time, P2 and P3 both showed up, so P1 gets preempted and sent to the back of the line. Who's at the front now? P2. So P2 gets to run for its 2 units, taking us to time 4. Okay, we're at time 4. And look, P4 has just arrived. But first, P2's time is up, so it goes to the back of the queue. P3 is next in line. It runs, and hey, it only needed 2 units of time anyway, so it runs to completion. It's finished, so it just exits the system and doesn't get added back to the queue. And we keep this cycle going, running, getting interrupted, going back to the queue over and over until that ready queue is totally empty. And this is our final Gantt chart. It shows the whole story. You can see how a long process like P1 had to run in 3 separate bursts, while a short little process like P4 finished in 1 go. The whole job is finally done at time 12. So, we did it. We created a schedule. But was it a good schedule? Was it efficient? To answer that, we need a way to measure its performance. And we usually do that by looking at how long each process was forced to just sit around and wait. There are 3 big metrics we care about. First, turnaround time. That's the total time a process hangs around in the system, from the moment it arrives until it's completely finished. Then there's waiting time. How much time did it spend just waiting in that ready queue, not running? And finally, response time. How long did it take for the process to get its first turn on the CPU after it arrived? So now, using our Gantt chart, we can actually calculate all these numbers. Let's take P1, for example. It finished at time 12. It needed 5 units of CPU time to do its work. That means it spent a whopping 7 units of time just waiting in line. Now, looking at each process is useful, but we often want a single number to judge the whole schedule. And a really common one is the average waiting time. If we average it out for our 4 processes, we get 4.75 units. And this brings us to what is maybe the most important decision you have to make when you're using round robin. All of those performance numbers we just calculated, they depend almost entirely on one single variable, the size of that time quantum. So let's just quickly recap the pros and cons here. The biggest advantage by far is fairness. Every process gets a turn, no one starves. That makes it amazing for interactive systems. But the big disadvantage is that its performance is totally at the mercy of the time quantum. And all that switching back and forth, well, that creates a lot of work for the OS, which we call overhead. So that leads us to the million-dollar question, right? What is the perfect size for the time quantum? And the honest answer is, there isn't one. It's all a trade-off. Okay, let's say you make the time quantum super, super small. The system will feel incredibly responsive because it's switching between tasks so fast, but the hidden cost is huge. The operating system ends up spending more time just managing the switching than it does doing any actual work. That's what we mean by high overhead. On the other hand, if you make the time quantum really large, you reduce that switching overhead, which is good. But now the system feels slow and sluggish. And if you make it way too big, well, round robin just turns back into plain old first come, first serve, and you lose all the benefits of fairness and preemption. So let's lock in the 3 things you absolutely need to remember. 1. Round robin gives us that illusion of multitasking by being fair and using a timer. 2. The whole system relies on a ready queue and that time quantum to make sure no process gets left behind. And 3, and this is the big one, choosing the size of that time quantum is a critical balancing act between making the system feel fast and making it run efficiently. You know, round robin is great because it treats every single process as an equal. But should it? What if you're rendering a 4K video but also just typing in a notepad? Should they really get the same share of the CPU? This leads us to the next big topic in scheduling. If you're curious how an OS deals with this, you should definitely check out priority scheduling next. Thanks so much for watching.